All right, let's talk about 7.3, the law of cosines. Um, so we need this law in order to solve the last two cases. So remember back in 7.1, we talked about four different cases, four different types of information you could be given about a triangle. And based on those four different types, we employ different strategies for solving triangles. For the last two types, side, angle, side, and side, 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 the law of sines doesn't help us, and so we need the law of cosines for that. So the reason for that is, I mean, if you imagine that you've got a triangle, and you know a side, an angle, and another side, right? So that's the information you're given. Now, law of sines isn't going to help here because law of sines will say something like sine of this angle over this side equals sine of, say, this angle over that side. But if you try to set up that equation, you're going to have two pieces of missing information because you don't know this side and you don't know this angle, right? Same thing goes for any other kind of combination of the law of sines that you could think of. You just don't have enough information here to use law of sines to solve this triangle. And obviously you'll have the same issue if you're given side, side, side information, right? So side, 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 so you know the three sides of the triangle, but you don't know any of the angles. So again, you're not going to be able to use law of sines because law of sines, requires you to know at least one of the angles. So we're going to introduce law of cosines. So there's a new fact in town that'll help us to solve these last remaining cases. So this is the law of cosines. And the law of cosines, as it turns out, is it's just an extension of the Pythagorean theorem. And you'll see what I mean when we write this down. So law of cosines says, for any triangle ABC, if the angles are capital A, B, and C, then the sides are lowercase a, B, and C, right? So for any triangle ABC, we have a squared equals b squared plus c squared minus 2bc cosine A. You might look at that and say, well, that doesn't look like Pythagorean theorem at all, but it is related. We also have two other statements that are true. So b squared equals a squared plus c squared minus 2ac cosine b. And c squared equals a squared plus b squared minus 2ab cosine c. So the reason I say that this is an extension of the Pythagorean theorem is that if you look at the last equation, you'll notice that if you ignore the 2ab cosine c, you have c squared equals a squared plus b squared, which we know is true if ABC is a right triangle. And if ABC is a right triangle and C is a 90-degree angle, and that would mean that cosine C would be 0. So this whole thing cancels off, and sure enough, right, you get the Pythagorean theorem. So if C is a 90-degree angle, then you get this last statement here, c squared equals a squared plus b squared. But these facts here, they're true for any triangle, right? It doesn't have to be a right triangle. These facts apply to any triangle ABC. And so we'll prove the first statement, right? The second two statements, the proofs of those are very, very similar to the first one. So I'll just prove the first one, okay? What we're gonna do is we're gonna draw our triangle on a coordinate system, and we're gonna draw it such that A is right at the vertex and that B is on the x-axis. So given any triangle, you can always kind of move it around and place it so that the vertex, so that A is right at the origin, and then rotate it so that B also falls on the x-axis. So I'm going to call, or not B, but angle C rather. So I'm going to call this angle A. I'm going to call this one angle C, and then B, would be somewhere up here. If this were obtuse, then B might be over here in quadrant 2, but it doesn't matter if B is in quadrant 1 or quadrant 2. What we're about to write down will work in either case. So this is our triangle right here. So A is obviously the origin, 0, 0. Now, if this is angle B up here, then this is side B down here. That means that point C is the point B0. Okay. I'm going to call this side A, right, for obvious reasons. And I'm going to call this side C for obvious reasons. Now, point B, it's a little bit more difficult to say what those coordinates are. We're going to write them down in a second, but for now, let's just call them X, Y. And then let's figure out if we can write down in terms of A, B, and C what X and Y are. So to do that, I'm going to give myself a little right triangle. And then I'm going to look at angle A here. I'm going to say sine of angle A. Well, if this is the point XY, then this distance here is Y, right? So sine of A would be Y over C. And if you solve for Y, then you would multiply both sides by C, and you would get Y equals C sine A. Then I'll do the same thing with cosine, right? Cosine A. Well, again, this is the point xy, so that means this distance from here to here should be x, right? So cosine of A is going to be x over C. Solving for x equals C cosine A. Okay, so let's figure out what the distance is. Well, let's figure out the length of side A here, right, using Pythagorean theorem. Or distance formula, I guess. We'll say, so A, using the distance formula, A would be the square root of x minus b squared plus y minus 0 squared, okay? And again, that's just the distance formula. But I can replace x with c cosine A, and I can replace y with c sine A, right? So this is going to be the square root of c cosine A minus b squared plus c sine A squared. C sine A minus 0, right, squared. Very good. What I'm going to do now is square both sides of this equation so that I cancel that square root. And now this will start looking really familiar, right? So we get a squared equals. I'm going to go ahead and expand this as well, right? So we would write this out twice and then FOIL it. I'm just going to do that in my head. If you need to do it, if you need to see it by hand, then by all means, pause the video, write this out twice, and then FOIL it out. But what we're going to get when we multiply this out is c squared cosine squared A minus 2bc cosine A plus b squared. Okay, so that's that first expansion. The second expansion doesn't involve any sums or differences, right? So you can just distribute the exponent there and call this c squared sine squared A. All right. What I notice is that I've got a sine squared and a cosine squared, and anytime I have that, I'm thinking of the Pythagorean identity, right? Sine squared plus cosine squared is 1. I'm just going to rearrange the equation a little bit so that we can see that a little more clearly, right? We have a squared plus, a squared equals c squared times cosine squared A plus sine squared A. Right? So that's bringing these two terms together and factoring out the c squared, right? So then I've got c squared times cosine squared A plus sine squared A. Then I'm going to bring this b squared closer to c squared, and then I'm going to leave the minus 2bc cosine A off to itself. This thing is just 0, Pythagorean identity, and I think we get the statement now, right? C squared times 1 is, of course, just c squared, right? We have a squared equals c squared plus b squared minus 2bc cosine A, sure enough, right? So there's the first statement, right? As I said, the proof of the other two statements is very similar. It goes very similar to this. Hopefully that's enough to convince you that it's true. What I want to do is just give you a couple examples of law of cosines in action. So we'll solve a couple triangles using law of cosines now. So let's solve triangle ABC if we're given this information. So let's solve ABC if A is 42.3 degrees, little b is 12.9 meters, and little c is 15.4 meters. Okay. Go ahead and pause the video, see if you can work this out on your own. Draw a picture. If you draw a picture, I think what you're going to find is that we've got a side angle side situation here. So you'll have to apply law of cosines, at least on your first step. And then after you have some more information, you might be able to apply law of sines or something else, right, to finish solving. But I'll let you pause the video, see if you can work this out. Okay, here's my solution. Again, I have no idea what this triangle really looks like. So I'm just drawing a little sketch here to help me organize the information, right? I know that side B is 12.9 meters. I know side C is 15.4 meters. And remember, we always label the sides opposite of the corresponding angle, right? So if this is angle C, then side C is over here opposite. And if this is angle B, then side B is down here. Anyway, and then we know that A is 42.3 degrees. So sure enough, right, a side angle side. I'm applying law of sines, not going to help here. I'll have too much missing information in order to use law of sines to solve for anything. But what I can do is use law of cosines. Since I know angle A, I'm going to use the version of the law of cosines that uses angle A, that uses cosine of A in that rule. And that would be the very first one that we just finished proving, right? So this is the law of cosines that I'm going to apply. It's this very top one. So I'm going to say A squared equals B squared plus C squared minus 2BC cosine A. So let's plug in some information and see if we can solve for anything, right? We don't know little a, so I have to leave that alone. But we do know that B is 12.9, and we know that C is 15.4. And we know that angle A is 42.3 degrees. And that's that, right? You can just throw that into your calculator now and figure out what a squared is, and then take the square root and you've got a, right? I might do an additional like intermediate step and do 12.9 squared. That's 166.41. 15.4 squared is 237.16. And then this all is just multiplication. I'm just going to punch it into my calculator at the same time. 2 times 12.9 times 15.4 times cosine of 42.3. Make sure you're in degree mode. And that whole thing comes out to 293.87-ish. Okay. So this plus that minus that is, well, I guess here I did some rounding, so I should have said it's approximately, but this equals 109.7. That's a squared, right? So a squared is approximately that value. So that means that a would be the square root of 109.7. So I'm going to say square root now of that answer. comes out to about, let's do 3 sig figs. So this is about 10.5 meters, right? 10.5 meters. Okay. I think that's as far as you're gonna get with law of cosines on this problem. I mean, you know this side now is about 10.5. Well, that's not true. Actually, now that you know this side, you could use law of sine, no, sorry. I was getting ahead of myself. Yeah, that's all you can do with law of cosines. No, that's still not true. You could still use law of cosines. Since you know all 3 sides, you could still use law of cosines to get the other 2 angles. Or you could use law of sines. I think law of sines is a little bit less cumbersome to work with. That's just a personal preference, I suppose. But since I know this other side, I'm going to use law of sines to get one of the missing angles. Once I have the second missing angle, I can get the third one just by subtracting the sum of the other 2 from 180, right? So law of sine now. I'm going to say sine 42.3 degrees over 10.5. Oh, I wrote this too high. Sine of, one of these days I'll get the hang of writing on this little dot cam. So sine 42.3 over 10.5 equals, let's say, sine C over 15.4. I can go ahead and solve for angle C now. So this means that sine of C equals 15.4 sine 42.3 degrees over 10.5. And that means that C is sine inverse of that stuff. Let's see about how much that is. So I'm doing sine inverse 15.4 sine 42.3. Again, make sure you're in degree mode. Divide by 10.5. And that comes out to about 80.8. Okay, so there's C. The last thing I need is angle B, right? That's the last piece of missing information. So I can say something like this. I can say B is approximately 180 minus A minus C. That's 56.9 degrees. And there we go, right? So we've solved the triangle. And that's how those ones go pretty much. Like I said, you could have used, instead of using law of sines at this step, you could have used law of cosines a second time. That would have been fine. You should end up at the same place. Okay? So that's it for that one. Let's do another one. So again, let's solve triangle ABC. This time, if A equals 9.47 feet, B equals 15.9 feet, and C equals 21.1 feet, you'll notice right off the bat, you don't have any angles given to you, right? So this must be a side, side, side situation. So you can use law of cosines on this again, because law of sines isn't going to help you, at least not for your first step, right? So, so go ahead and pause the video, see if you can work this one out on your own. Okay, so here I go. You have all three sides. And if you look back at the law of cosines, right, in each case, you need to know the three sides and you need to know an angle in the triangle. Or rather, you need four pieces of information. You need three pieces of information, right? You're allowed to be missing one of the pieces of information so that you can solve for it. And so in this case, we have all three sides. We just don't have any of the angles. But what that means is that we can use any of these. We could use any of these three versions of the law of cosine as our first step. It really doesn't matter which one you decide to use on your first step. So I'll use the top one again. Right, I'll use the first one again. It served us well last time. We might as well use it again. So we'll say a squared equals b squared plus c squared minus 2bc cosine a. So 9.47 squared equals 15.9 squared plus 21.1 squared minus 2 times 15.9 times 21.1 times cosine of a. Okay. So I'm kind of disinclined to to punch anything into my calculator just yet. I'm just gonna, what I want to do ultimately is solve for a, right? So I might just do that symbolically without punching the numbers into my calculator. I'm just nervous that if I punch it in now, I'm gonna get all kinds of rounding errors. Maybe it's not such a huge deal, I guess, to do that when you're just squaring the values, but anyway, here we go. Yeah, maybe I'll punch them in. So 9.47 squared is 89.6809. 15.9 squared is 252.81. 21.1 squared is 445.21. And then we have 2 times 15.9 times 21.1. That's 670.98 cosine A. All right, I'm going to combine these and move them over. I'm not going to like show each individual step, but we have 252.81 plus 445.21. That's 698.02. And I'm going to do 89.6809 minus 698.02. That comes out to negative 608.3391 equals negative 670.98 cosine A. And I'll divide by the negative 670.98. So divide by negative 670.98. That comes out to 0.9. Oh, how many decimals do we have? A bunch. Yeah, well, okay, so maybe this is where I'm not going to write down the decimal. I want to keep the exact answer. So here's what I'm going to say. I'm going to say cosine A equals, the negatives will cancel though, so I'm going to say 670.98. Sorry, I was going to do that in the wrong order. Let me try again. Cosine A equals 608.3391 divided by 670.98. That means A is cosine inverse of that stuff. That's what I'm going to punch into my calculator, so I don't have any rounding errors. And to 3 sig figs, that's Oh, well, to 3 sig figs, that's 25.0 degrees. Okay, so now I know that this angle right here is 25.0 degrees. Okay. So again, at this point now you have a couple options, I think, to solve for the second angle. You can apply law of cosines again using one of the other versions. So you could say something like b squared equals a squared plus c squared minus 2ac cosine b, right? And then solve for angle B that way. And then once you have angle B, then you can use it. You can just say 180 minus that equals angle C, and then you're done, right? So that's one option. Another option is, so you could do that, or you could do the same thing with angle C. Use law of cosines to find angle C, or whatever. Another option would be to use law of sines at this point, right? So again, you can say sine 25 over 9.47 equals sine B over 15.9, and then solve for angle B, right? Again, I think that, for me, I think it goes a little quicker that way. So that's what I'm going to do. I'm running out of space. So I'm going to say, oh, what did I say? Sine B over 15.9 equals sine A over 9.47. So then B is sine inverse of 15. So if I multiply both sides by 15.9 and then take sine inverse, right, I get 15.9 sine 25 over 9.47. That comes out to about 45.2 degrees. There's angle B. And then angle C, I've run out of space. Oh, maybe I can squeeze it in like right over here. So angle C. Since I know angles A and B already, right, I can say, well, angle C should be 180 minus 25 minus 45.2. 109.8. All right. And there you go. So that's how you solve a side-side-side triangle. So law of cosine is pretty nice. It gives us another tool in our arsenal that we can use to solve some of these triangles and stuff. Okay. Let me give you one more example. Kind of, sort of application, although it's not like a real world situation. I say in air quotes. But let's look at another example. So this one says the sides of a parallelogram. Sides of a parallelogram are 4.0 centimeters and 6.0 centimeters. One angle, one angle is 58 degrees, while another is 122 degrees. Find the lengths of the diagonals. So find the lengths of the diagonals of the parallelogram. So the sides of the parallelogram are 4 centimeters and 6 centimeters. One angle is 58 degrees, while another is 122 degrees. Find the lengths of the diagonals. I'll get you started with the drawing because you may not remember what a parallelogram looks like. A parallelogram is just, it's a quadrilateral, so it has 4 sides, and opposite sides are parallel. Right, so it's got to look something kind of like that. Well, if you pretend that these sides are parallel, they should be. Some things that we know about parallelograms are that, well, these are transversals, right? It's like you've got parallel lines here and a transversal there. So these two angles are the same, and these two angles are the same. And they're telling us that one of them is 58 degrees and the other is 122. So I'm gonna assume that this one's my 58 degree angle, and this one's my 122 degree angle. We're also told the sides of the parallelogram are 4 centimeters and 6 centimeters. And then we're being asked to find the diagonals. So what we want to find are the lengths of the diagonals, right? These things here. Okay, yeah, you can hear my kids in the background probably. Anyway, the sides of the parallelogram are 4 centimeters and 6 centimeters. I'm trying to figure out if we can tell by looking at it which side should be 4 and which side should be 6. Is there a way that we know that? Well, if one of them was really small and the other one was really long, what does that do to our... I don't know how that relates to the angles that were given. I'm not sure if, because you could have these same angles and make this side really short or really long. I don't know if we have enough information to tell you the truth, to know which one should be 4 and which one should be 6. Maybe it doesn't matter. I don't know. I'm going to call this one 6. I'm going to call this one 4. And maybe it doesn't matter. We'll see. We'll see. Okay, here we go. So we want to find the lengths of the diagonals here. So, of course, if this is 6 and 4, then this is also 4. This is also 6. And thinking of this triangle here, I've got a side angle side. So I can use law of cosines to finish solving the triangle. What I really want is, of course, that side length there. So if I can use some version of the law of cosines that'll allow me to solve for that, then that would be ideal. And I think I can, right? If I say, let's label this A, B, and C. So if I say, I'm going to use the version of the law of cosines that involves angle A. So that one would be the first one on the list. A squared equals B squared plus C squared minus 2BC cosine A. And A is the thing that I'm looking for, right? So I can say A squared equals B squared. Sorry, A squared equals B squared plus c squared minus 2bc cosine A. And yeah, so now that I'm working it out, it doesn't matter which one you call 6 and which one you call 4. Worst case scenario, if we switched these around and called this one 6 and this one 4, then we would be saying 4 squared plus 6 squared minus 2 times 4 times 6 cosine 58. But you're going to get exactly the same result, right? So that must be why it doesn't matter. Anyway, so a squared is 36 plus 16 minus 12 times 4, 48 cosine A. Or cosine 58 degrees. Let's punch this into our calculator. 36 plus 16 minus 48 cosine 58. So a squared is approximately 26.5639. If we take the square root, then we see A is approximately, so it looks like we have two sig figs. So we'll say A is approximately 5.2 centimeters. Wait. So A is approximately 5.2 centimeters. So that's that one. And we can do something similar for the other diagonal. So I've got to use different letters now. So A, well, maybe I'll just call this one B2. So A, B, C. This time, this is the angle that I know, right? I know it's 122 degrees. So I'm going to use the version of the law of cosines that involves angle C. That would be this one, that C squared equals A squared plus B squared minus 2AB cosine C. So C squared equals 4 squared plus 6 squared minus 2 times 4 times 6 times cosine of 122 degrees. So it's almost identical to the previous problem, but instead of 58 degrees, now we have 122 degrees. Okay. 16 plus 24 minus 48 cosine 122. I'm going to go ahead and just cut to the chase and take the square root of all this stuff. So I've got square root 16 plus, oh, not 24, 36, I'm sorry. Square root of 16 plus 36 minus 48 cosine 122. And that comes out to about 8.8 centimeters. Okay, and there we go. So that's that one. Okay, I think once you draw a picture and kind of get going, it's not too terrible. That'll do it. That's all I want to talk about in this section.